All right, this is one of our shapes. Imagine that it's symmetric, a little bit like if an egg was symmetric. And then we've got a cone. And this is like an hourglass figure or a smokestack. This is two bowls that are opening up but in opposite directions. And by the way, these are supposed to go up and down forever. This one is fully enclosed. So this is a finite object. These are infinite objects. This one is infinite as well. And there's one more shape. It's the best one. It's a Pringle chip or a saddle. So when I said best, what I really meant is it's the most complicated. It's really the hardest to visualize and think about, but what I'm thinking of here is a saddle-like thing. So if I cut it right here, I would have a parabola opening down. And then if I cut it here, I would have a parabola opening up. This keeps going down forever. It keeps going out forever to the left and the right, and it keeps going up forever.
So those are the 5 shapes we should study.
These are the other 5 besides this one. So we already said this one was, what was the name for this?
Paraboloid.
It's a paraboloid, and specifically what kind of paraboloid is it? Elliptic. Good. Let me go ahead and write down the equation for this one, and then I'll give you a list of equations, and you can help me figure out which equation goes with which picture over there. So this one looked like this. Is equals x squared plus y squared. Okay, over here, one type of shape we could have is we could take that exact same equation but change either the y to have a negative coefficient or the x to have a negative coefficient. We could have whoops, meant to make that a z at the end. We could have something like this. Remember the equation? Do you remember the equation for a sphere?
It's x minus a squared plus b plus y minus b squared plus z minus c squared equals the radius of the sphere squared.
Good. So it looks, this would be a sphere if this said plus z squared. If it's minus z squared, it changes things. And we'll think about how that changes things. You could have something like this. So this time I have all pluses. Oh, I keep writing down the wrong variables. I wanted to have all 3 variables there. In this case, I have all 3 of them squared, and all 3 of the coefficients are positive. This one is identical to this one, but this number, this constant on the other side is negative instead of positive. That changes the shape. And then here's another one. exactly same as this one and this one, but with a 0 on the right. So these three look very similar. The only thing that's different is the constant on the right-hand side. So which three surfaces do you think those might give us out of these three on the board? Can you tell? It may be hard to tell before we talk about the traces.
The fifth one is it's a cone.
Okay. Why do you think that's a cone?
Because it's equal to 0. So it inevitably it forms the top half of the cone, and the 0 forces it to form the bottom half of the cone.
Okay. Do you think you could tell me why it makes it form the bottom half of the cone?
You have the negative c squared right there, and so it's branching out both x and y in a positive, but because of negative c, you get the bottom half.
Okay, I'm not making the connection between what you're saying and how the picture looks. So I understand you're saying because of the negative z, you're getting the bottom half. But what does that have to do with the 0?
It's not too sure about
Okay, that's okay. It does give us the cone, so you're right about that. This will give us a cone. It will become more obvious when we think about what the traces are. So let's start with that one. Let's think about the traces of this. I'm going to go ahead and erase this elliptic paraboloid. All right, so the traces for number 5. Let's plug in z equals k first. So x squared plus y squared equals k squared. Good, these are circles. The radius is k, or absolute value of k. And what happens at z equals 0?
At the origin. Well, when 0, you need a circle with the radius 0 at the origin.
That's right. You have a circle with radius 0 at the origin, so that's just a point at the origin. That's why this is coming to a sharp point. If this is centered around the z-axis and this is centered around the z-axis, and notice they won't hit the origin. This one won't either. This one could hit the origin. Sticking with the same one, let's plug in x equals k, or I'll plug in y equals k first. So I get x squared minus z squared equals negative k squared. I'm going to multiply everything by -1, so I get a positive k squared on the right. All right, what does this 2D curve look like? K is a constant, and x and z are variables. So, for example, what would this look like? Y squared minus x squared equals 1. If I graph that on the xy plane, this is the type of object that you probably haven't worked with very much, but you may remember what it is. Does anybody remember? It's not a parabola, right? It's not a circle. But it is a conic section. Have you heard of conic sections? Conic sections are curves that you get when you take a plane and you slice through a cone. So if you slice this horizontally, you get an ellipse or circle. If you slice it half of it, you get a parabola. Or I guess if you slice this way, you could get a parabola. And then if you slice vertically, what's the shape that you get? This isn't a parabola because there's two pieces. Do you remember what this thing is called? Looks like that. Yeah, it's a hyperbola. Good. All right, so if the curve looks like an ellipse except for the signs out in front, the coefficients of x and y have opposite signs, then you've got a hyperbola. And what's happening here when you cut the cone with y equals k is you're getting this hyperbola, or hyperbolas like these. What happens when you cut with x equals k? Good. You just get another hyperbola. So for this one, if we cut with an x equals k, if I imagine I'm cutting with a plane that's parallel to this wall, but out a little bit, then the hyperbola will look something like this.
For the hyperbola, for the x and z, those are hyperbolas that are parallel to the xz plane, right?
This one?
Yes.
That's right. They're parallel to the xz plane.
Can you draw that in 3 dimensions? Just attempt it.
Yeah.
I'm trying to visualize this.
Yeah.
It's a little difficult to imagine.
So I'm thinking of this as the xy plane. And then the xz plane is,
So it's like coming at us almost.
that's right, it's coming at us. So if I think of that as the origin over there, and the z-axis, then the xz plane is that wall over there.
Yeah.
And so these green hyperbolas are on walls that are coming out straight at us from the board.
I'm trying to see it. It's on the XC plane, and it's parallel to the XC plane, but it's just being drawn across the Y axis. Okay.
Yeah.
I'm just trying to find a way to see how we draw it without screwing up.
Oh, that's good. So if this is y equals k, the plane is going to look something like this. And I'm imagining this plane hits the y-axis here, and it hits this 3D object right there and right there. So what can we say about these two then? Number 2 and number 4. if we think about the traces of number 2, for example, if we plug in z equals k, then we'll get 1 plus k squared. So what does this give us? Yeah, it's a circle. The radius is the square root of 1 plus k squared. If we plug in k equals 0, then we get a circle with radius 1. That's happening here. And the hyperbolas, if you take the traces with x equals k or y equals k, you're still getting the same hyperbolas that you got in number 5. So these hyperbolas that you're getting here are still here and here. Same thing for this shape. You're still getting hyperbolas if you cut it with an x equals k or y equals k. So I'm thinking of hyperbolas that look like this. But the difference is what happens when you cut with z equals k. So here, if you cut with z equals 0, you just get a point at the origin. Here, if you cut with z equals 0, you get a circle with a positive radius. Here, if you cut with z equals 0, no solution, good. And you can see that happens here. If I plug in z equals 0, x squared plus y squared is -1. So I get a circle with radius, well, I get no solution there. All right, so this is number 4. And this is number 2. Number 5. We do call this one a cone. In general, though, all 3 of these shapes have 2 hyperbola traces and 1 ellipse trace. So since there's 2 hyperbolas, we call them a hyperboloid. And the only thing distinguishing this one and this one is that, the main thing is that this one is 1 piece and this one is 2 pieces. So usually people will call this a hyperboloid of 2 sheets and this one a hyperboloid of 1 sheet. But hyperboloid will work there, or you could even say elliptic hyperboloid. All right, out of the remaining equations, 1 and 3, which one do you think is this egg? Which one? Okay, number 3. What do you guys think? You think this is number 3? Based on the traces? What types of traces are you going to get?
All spheres or circles.
Okay, all circles, not quite circles. What are they technically?
Ellipses.
Yeah, all ellipses. And this will give you all ellipses. If you cut it horizontally or vertically, you'll get ellipses. So good. This is number 3. And if they're all ellipses, then what do you think we call this?
Ellipsoids.
Yeah, we call it an ellipsoid. Good. All right. That leaves the best one, the most complicated one. So let's quickly think about the traces here. If I plug in z equals k, what do I get?
Hyperbola.
Yeah, good. If you plug in z equals k, you get a hyperbola. And you can see that here. If I cut with a horizontal plane, And my trace looks something like this. What happens if I plug in x equals k? For example, if you plug in x equals 0 into this.
It's gonna be a downward.
Yeah, good. It's a parabola opening down. If you plug in y equals 0, you get a parabola opening up. So you see that right here. If you plug in one direction, you get a parabola opening down. If you plug in another direction, you get a parabola opening up. This is a little harder to draw with a 3D coordinate system like this. I usually just sketch it like this, and then put my axes on it after I've sketched it. Those are the basics on these surfaces, and I want you to be able to figure out which is which out of all 6 of these. These are the only 6 that you need to know. And then, you need to know how to do cylinders. Those are more simple.
So for number 3,
Yeah.
is that a one-sheet hyperboloid?
This one?
No, sorry, the equation.
Okay.
3.
Yes, this is a hyperboloid of one sheet.
Okay. So the 6 basic shapes being cylinders, paraboloids, both hyperboloids, both 1 and 2 sheets, ellipsoids, and columns.
Yes. So the 6 basic shapes are these, and then on top of those 6 basic sheets, there's the cylinders. So here's 5, and then the one that we had before that was the cup. That was the other kind of ellipsoid. Oh, I didn't ask you about this name. What do you think is the name of this one? We have 2 parabolas. So we'll call it a paraboloid. But what kind of paraboloid will we call it? Yeah, hyperbolic. Remember the other one was an elliptic paraboloid?
What's the equation for the hyperbolic paraboloid?
The equation was number 1. Thank you for asking. So I think these look a little intimidating at first, and especially if you try to memorize the equations, they're pretty challenging, but if you use traces, they're really not bad.